Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. Let us solve some exercises about the integral test, section 11.3. We said that if the function is continuous, positive, decreasing on the interval from 1 to infinity, then if the improper integral of this function f of x from 1 to infinity is convergent, then the series is convergent. If it is divergent, then the series is divergent. And also we have seen one important type of series, the P series, any series in the form from 1 to infinity, 1 over n to the power p. So n, which is the variable, is here and it is raised to some power. This is a P series, and the P series converges if p is greater than 1, and it is divergent for the values of p less than or equal to 1. So here, determine whether the series is convergent or divergent. I need to find an, the nth term of this series. I need to write it in this form. So let me see, the first term is 1 if I deal with it as a sequence. So the first term is 1, the second term is 1 over 8, the third term is 1 over 27. So the fourth term is 1 over 64. Now try to, uh, the nth, what would be the nth term? Okay, this is 1, always 1. Even this one, you can write it 1 over 1. So what do we have here? Okay, 1, we have 1. 2, we have 8. 8 is 2 to the power of 3, isn't it? 3, we have 27. 27 is 3 to the power of 3. Okay, 64 is 4 to the power of 3. 125 is 5 to the power of 3. So if we have 2, we have 2 to the power of 3. If we have n, we have n to the power 3, because 4 to the power 3. So this series is summation from 1 to infinity of 1 over n to the power 3. If you put n 1, you get 1 and so on. So does this series converge or diverge? Well, this is a P series with P equals to 3 greater than 1. So this series is convergent. That's it. Okay. Here, if you remember, this is written on this form. So it's one of these series. It is 1 over n ln n, where p is 1. So I know that it is divergent, but I need to prove it, and I know that I have to use the integral test here. So immediately I consider the function f of x 1 over x ln x. And I can see that the domain of this function is from 0 to infinity. So from 2 to infinity, f is continuous, positive on 2 to infinity. And let me find f prime. And f prime is x squared ln x all square negative the derivative of x ln x, because the derivative of 1 over u is negative u prime over u square, chain rule. So derivative of x is 1, so I have ln x plus x times the derivative of ln x, which is 1 over x. So this is ln x plus 1 over x squared ln x to the power 2. Now x squared is always positive, ln x squared is always positive. This negative will make f prime negative only if, so f prime would be negative, where when ln x plus 1 is positive. So if ln x plus 1 is positive, then f prime would be negative. Let us solve this inequality. Ln x is greater than negative 1 raised to the base e. So x is greater than e to the power -1. Well, 1 over e is a small number, okay, 0 0.4, about 0 0.4. So if prime is negative in this interval, so f prime would be negative in the interval to infinity. So f is decreasing on the interval from 2 to infinity. All right. Now let us consider the improper integral from 2 to infinity of this function 1 over x ln x dx. And the improper integral by definition is limit when t approaches infinity from integral from 2 to t 1 over ln x dx. Well, let us think of this integral. How do we evaluate this integral? Well, if I take ln x u, then 1 over x dx would be du. And then the indefinite integral would be 1 over x dx as du, and 1 over ln x is u, so over u. The integral is ln u, alhamdulillah, so it is ln x. Of course, x starts from 2, so ln x is positive in this case. That's the graph. After 1, ln x is positive. So no need to use the absolute value. So this would be limit t goes to infinity. The integral is ln x from 2 to t. So ln t minus ln 2. Well, ln infinity is infinity, ln infinity is infinity, so this is infinity minus anything is infinity, so the integral diverges. So by integral test, this here is, this is an, so this here is summation an from 2 to infinity diverges. And this is what we know from this remark, but this is the proof, okay? Ln n over n square. Well, again, this is an example about this one, ln n over n to the power p, and I know it's convergent from this remark, but it is not enough to say it's convergent, okay? You have to prove it using the integral test. So this remark is for you to know that I will use the integral test for such series. So immediately you can consider the function f of x, which is ln x over x squared, and determine the domain of the function. 0 is not in the domain, and I have ln x from 0 to infinity. And I need it from 2 to infinity, so f is continuous positive from 2 to infinity, because ln n is positive, x squared is positive, after 1 ln x is positive. So let us consider the derivative. I will use the quotient rule. Derivative of ln x is 1 over x times x squared minus derivative of x squared is 2x times ln x. So I can cancel x with the square, so I still have x here. I can take it as a common factor. So I have 1 minus 2 ln x over x to the power 4. I cancel 4 with x. I still have 3 power. So this is the derivative. 1 minus 2 ln x over x cubed. Well, x cubed would be the 0 of x cubed is 0. And from 2 to infinity, x cubed is positive. All right. from 2 to infinity, x cubed is positive. So the sign of f prime in the interval from 2 to infinity depends on the sign of 1 minus 2 ln x. So f prime of x would be less than 0, okay, in the interval 2 to infinity. Let me say in 2 to infinity. Maybe it's not the same interval, but I'm telling you that we are searching from 2 to infinity. If 1 minus 2 ln x is negative, if this is negative in this interval, then f prime would be negative. And this means that 1 is less than 2 ln x, or ln x is greater than 1 over 2. So x is greater than e to the power half. Well, what is e to the power half? It is 1.6. That's good. So from 1.6 to infinity, f prime is less than 0. So f is decreasing on the interval 2 to infinity because it's decreasing from 1.6 to infinity. That's excellent. So let us consider the improper integral of ln x over x squared from 2 to infinity. By definition, this is the limit of the integral from 2t to t, where t goes to infinity, of ln x over x squared dx. And now let us think of this integral. How do we evaluate this integral? The derivative of ln x is 1 over x, but we have x squared. So I will consider this integral. I will write it as x. Of course, 1 over x squared is x to the power negative 2 times ln x dx. And if you studied chapter 7, you know by heart now that we solve this integral using integration by parts. We take u equals ln x, du would be 1 over x dx. For integration by parts, check section 7.1, I believe. And dv is x minus 2 dx. So v would be the integral of x to the power negative 1 over negative 1, or just negative 1 over x. So this integral, let me call it I, would be equal to uv, so negative ln x over x, minus integral v du. And v times du would be negative, so this would be positive 1 over x squared dx. So the final answer would be negative ln x over x, and integral of 1 over x squared is negative 1 over x. So that's it. So this would be equal to the limit. The integral now is negative ln x over x minus 1 over x from 2t to t. So this is the limit from t to infinity of negative ln t over t minus 1 over t, okay, minus negative ln 2 over 2 minus, and there is a minus outside, so plus 1 over 2. Now if I take this t to infinity, 1 over infinity would be 0. But here I will get negative infinity over infinity. So when I get negative infinity over infinity, I have to use L'Hopital's rule. So let me consider limit negative ln t over t when t goes to infinity. It is a negative infinity over infinity, so I use L'Hopital's rule. Derivative of ln t is 1 over t, derivative of t is 1. So negative 1 over infinity, so that's 0. 1 over infinity is 0. So this limit is also 0. Okay. by here. You have to write this, okay? You have to prove that this limit is 0. Now, what is the answer? So the limit would be what? Negative times negative, it's ln 2 plus 1 over 2. I can write it like this. Ln 2 plus 1 over 2. So the integral converges. So by integral test, this series where this is an from 2 to infinity of an converges. And we know it is convergent, but we needed from here, but we needed to prove that. Good. What about this series? Well, let me consider the function x over e to the power x. This is k n e to the power negative n or k e to the power negative k. This function is positive continuous on the interval from 1 to infinity here. K starts from 1. And the reason, because the domain of the function is all real numbers, because e to the power x is always positive. So no zeros of the denominator. So the domain all real numbers. So this function is continuous everywhere, but from 1 to infinity it would be positive. No, it's not positive everywhere, because if x is negative it would be negative. But from 1 to infinity it's positive. So let me check the derivative. Let me use the quotient. I can use the product, it's no problem. Ex squared, derivative of x is 1 minus the x times ex. Well, I can take ex as a common factor and cancel it with the one of the two below. So the answer actually is 1 minus x over ex. Well, ex is always positive. So f prime is less than 0 if 1 minus x is less than 0. And this means that 1 is less than x or x greater than 1. That's fantastic. So f prime is less than 0 when x is greater than 1. So f is decreasing on the interval 1 to infinity. The three conditions are satisfied of the integral test. So I consider the integral from 1 to infinity of the function f of x dx. And by definition, it is the limit. When t approaches infinity, integral from 1 to t, x over ex dx. And now it's time to think, how can we evaluate this integral? The derivative of ex is ex. So I believe that you know also by now that this integral can be evaluated using integration by parts. Even we can do it in the fast way where we write u and dv here. And please, for this, just review section 7.1. The function which we are calling u is x, the derivative is 1, then the derivative is 0. The function which we are calling dv is e negative x, integrating negative e negative x. Integrating, we get e to the power negative x. We write positive, negative, positive, and then we multiply these, and the answer would be negative x e negative x, negative e negative x. Okay, so that's the integral. So it is limit t goes to infinity of negative x e to the power negative x, negative e to the power negative x from 1 to t. All right. So this is negative t e to the power negative t, negative e to the power negative t, negative minus, and there is a minus here, so it would be plus 1 e to the power negative 1 minus, and there is a minus here, so it would be plus e to the power negative 1. Now, if I replace t by infinity, e to the power negative infinity is 0 because this is the graph of e. But here, I'll have infinity times 0. And because I have infinity times 0, I have to use L'Hopital's formula to find the limit of negative t times e to the power negative t when t goes to negative infinity. Because I have infinity times 0 in L'Hopital's formula, I need to write it like this. I need to take one of the functions below. So now if I replace t by infinity, I get infinity over infinity. And this means I can use L'Hopital's formula. Derivative of negative t is negative 1. Derivative of et is et. And now e to the power infinity is infinity, and negative 1 over infinity is 0. So this will also go to 0, but you have to show that. So the limit is 2e to the power negative 1, or just 2 over e. This means that the integral is convergent, and by the integral test, the series, uh, well, it is here ak, I believe, converges. So this is, just call this AK. The last exercise, the last example, similar to this one, but instead of negative k, I have negative k squared. Let us see what would happen. Will it make a difference? So let us consider the function x over e to the power negative x squared. Well, it would be negative x squared if it is in the numerator, but now I took it down, so it would be positive x squared. As you can see, this function is positive, continuous from 1 to infinity, because the domain, again, the domain of this function is all real numbers. I have no problem with e to the power x squared. It will never be 0, and it's not negative either. So let us find the derivative to test decreasing and decreasing, where it is decreasing. Okay, so e to the power x squared all to the power 2. Again, I'm going to use the quotients. Derivative of x is 1 times x minus x times the derivative of ex squared is ex squared times the derivative of x squared, which is 2x. Well, I can take e to the power x squared as a common factor, and I'll have 1 minus 2x squared, isn't it? Okay, over ex squared to the power 2. Cancel this with this, and I'll have 1 minus 2x squared over e to the power x squared, which is always positive. So f prime would be less than 0 if 1 minus 2x squared is less than 0. I need f prime to be less than 0. Well, this means that 1 is less than 2x squared, or x squared is greater than half. Okay, well, x squared is greater than half means x should be greater than 1 over square root of 2. Of course, uh, we can talk about the negative numbers here, but the negative numbers are not there. We are dealing with positive numbers from 1 to infinity. If you divide 1 over square root of 2, the answer is 0.7. So excellent. So greater than 0.7, f prime is negative. So f is decreasing from 0.7 to infinity, or what I need from 1 to infinity. So it satisfies all the three conditions. And now I can consider the improper integral of this function x over e x squared. Writing the definition of the improper integral. And now let us think of this integral. Well, the derivative of x squared is 2x. So this is a simple substitution. Just take u as x squared. Du would be 2x dx. So I need 2x for the indefinite integral. And I will divide by half outside. So it would be half integral du over eu. Or again, you can take it up and take negative x squared as u. The integral of e to the power negative u is e to the power negative u times minus or divided by negative 1. So the answer is negative 1 over 2 e to the power u, or e to the power x squared. So that's the integral. So it's negative 1 over 2 e to the power x squared from 1 to t. So its limits negative 1 over 2 e to the power t squared minus negative 1 over e to the power 1, which is e. Now e to the power infinity is infinity. 2 times infinity, negative 1 over infinity is just 0. And the answer is 1 over 2e. And the integral converges. And by integration test, the series summation from, this is ak, k 1 to infinity of ak converges. Thank you very much. I hope the integral test is easy for you by now.